So today we have been asked to continue our lectures on educational analytics, and we are considering the aspect of estimation indices or estimation techniques. So in our previous lectures we discussed the aspect of measurement scales and normalization, as well as standardization of our data sets. We give you the essence of doing that by emphasizing that your ability to determine the measurement scale will help you to predict the test statistics you want to use. Also, your ability to normalize and standardize your data will enable you to train your data that is unitless. Invariably, it will reduce any form of error or bias in the data sets. So now we are considering today the aspect of error estimations. Now we have experienced errors in scientific measurements, or we've also conducted error analysis in scientific measurements. So by error we mean the discrepancy that exists in your measurements, maybe as a result of a systematic problem or as a result of maybe random effects. So we have different types of scientific errors, like maybe error due to calibration, maybe systematic error like error due to the measuring instruments, or random error as a result of unpredicted a scenario that occurred during the measurements, maybe as a result of environmental factor or as a result of the observation bias, or any kind of discrepancy that could exist in the measurement. So as a preamble, we define error as the discrepancy between the exact value of a data set by the predicted value. So this is a typical expression of error. That means this parameter measures the difference between the exact value and the one you predicted, or the one you want to measure, or the difference between the observed value and the predicted value. So we also have the absolute error, as the case may be. We have absolute error. I think you can just take the absolute value on the error you've already obtained. That gives you the absolute error. Now the notion of this absolute error is to help you reduce the effects of where the error comes from, like the direction of where the error comes from. So here, once you introduce the absolute value, we will only consider the magnitude of the error in the process. So invariably, if you have a very large value as the absolute error, that means the discrepancy is much. But if you have a small value, the discrepancy is small. So for instance, in scientific measurement, if you want to measure maybe student performance, whereby there's going to be a repetition in the measurements, so there's bound to be some form of discrepancy. And how will you be able to identify those discrepancies is for you to go in and then compute the error. Now take for instance, if you want to measure student performance based on subjects, say x1, x2, x3 to xn, based on subject, maybe this is the performance in mathematics, this is the performance in physics, chemistry, and so on. So you can decide to use the standard error due to the mean, which is defined as the variation in the measurements from the mean divided by the square root of the sample size. which is n. You can obtain the standard deviation of this measurement x by using this simple computation n into summation x squared minus summation x all squared over n into n minus 1, and then you take the square root. This gives you a better estimation of the standard deviation of this data set. And note also the mean value is also important depending on the nature of the formula you want to use, which is summation xi equals to 1 to n divided by n. So this is the standard error that you can compute using this formula, and it gives you the error estimate or the discrepancy that you might have had in taking this measurement repeatedly. So if you have a small value of the standard error due to this measurement, we can now say, okay, the error is small enough, or is the data set is meaningful that we can use it for further decision making. So in some cases, if you have the exact value, maybe based on a standardized value in the measurement, say the standardized value is x exact, then you need to add the error value in all cases. So this gives you a better approximation to this data. In similar situation, we can also have the percentage absolute error in the measurement. This is typical example in a scientific measurement. You have the percentage absolute error defined as just you could divide this by the exact value x exact. That is the absolute value of x exact minus x predicted divided by the exact value. So since it is percentage, you multiply it by 100 factor. So this is another way of representing the error by obtaining the approximation and then noting how spread the predicted value is from the exact value. So the convention is that the smaller the percentage error, the more effective your measurement is, which can help you to make further prediction or further explanation about the data that you have taken so far. So this happened in scientific measurements, and we also have the similar scenario. In educational analytics and measurement as well. So the first estimation index that we are going to consider is the mean square error. Mean square error. Mean square error. The mean square error is defined as the approximation of the data set. This is the observed data set from the response data set, which I denote by yi cap, and then you square it. Now the data set was taken to be finite. It can run from 0 to n. But how did this come about? For instance, if you have been given the training set of the data in this space x1 y1 x2 y2 to xn yn, you can decide to use a transfer function, you can decide to use a transfer function. Say this is a transfer function I caret underscore I f of xi such that I runs from 1 to n. Now this transfer function is considered to be the algorithm is embedded in the algorithm that you want to use to determine or to predict the data set. So it is inherent in the hidden layer, so to speak, in that model. So some of these transfer function could be a sigmoid function, it could be a linear equation, it could be quadratic equation. It all depends on how you want to model these data sets. It all depends on how you want to model this data set. We consider this data set to be the training data set. Consider it to be the training data set at this moment, defined by this function where f is the transfer function. Obviously, this transfer function, for instance, if you want to consider student academic performance or factors that affect student academic performance, you can say that this function has several independent variables defined by xi. So you can say one of them is a motivation. You can say one of the factors that can improve or affect student performance is motivation. You can have interests. You can have attitude. You can have peer interactions and other factors that can be considered. So maybe they are finite and they helps you to predict academic performance. And they help you to predict academic performance. So the practical interpretation of this trained data is like, okay, we are going to consider all these factors. You measure these factors and then see how they will predict academic performance of the student, maybe in a particular subject, say mathematical sciences. Yes, so you know this measurement comes from different scale, which we had discussed before. It comes from different scale. Maybe you could have a cognitive styles, or the learner cognitive style, or cognitive ability. So this measurement comes from different scale. It could be from a questionnaire. It could be from tests. There are different sorts of different scales of measurement. Remember, you might have standardized the data set or normalize them, as the case may be, depending on the analytical function you want to use here or the transfer function you want to use here. So it will help you to predict this one. So this is a typical representation of this real life scenario in educational analytics. Now, the mean square error is going to approximate the difference between the response variable, the difference between this is the response variable, or you can call this one the exact variable. This is the exact variable, and this is the response variable, or this is the dependent, in this case, dependent variable that comes out from this independent variable here. This is the independent and this is the dependent. So it approximates by squaring the differences in mean between the exact value and the response variable. Conventionally, we say that the threshold, it should be less than 0.01 or less than 1% of the data range. It should be less than 1% of the data range. So this is very simple for taking measurements that are in continuous scale, but obviously your normalization was able to solve that problem. Now, the next one that we can consider is the root mean square error. The root mean square error. Root mean square error. Simple, it is the square root of the mean square error, and the threshold is like the previous one. So you only take the square roots of the mean square error, and then you obtain the root mean square error. I think this one is a better correction factor, or a better estimator than this, in the sense that it can reduce the possible effect of the outliers, because it now takes the square roots of this other estimation. Now, the next one that we should consider is the mean absolute error. We can consider the mean absolute error. Let me write this function up here, because it's going to be used as a reference point. The function we derive here looks like y caret equals to f of xi. So this is the response, and this is the predicted. Okay, we need to consider the second one, which is the mean absolute error. So the mean absolute error is going to approximate the absolute value of the response variable, the absolute value of the response variable here, y raised to bar, from the observed variable. So this is the response in this case, and this is the observed. Remember, this is similar to when we were calculating the errors in a standard scientific measurement. It's almost the same thing, but this is a better approximation by taking the average and then also taking the absolute value of the averages between the observed measurements and the response measurements. Now, the threshold is that it should be also less than 0.1. Now, some people consider it to be just less than the 10% of the data range. Now, if it is 0.01 or 10% of the data range, we now say that okay, the model is a perfect fit. The model is a perfect fit, be it a regression model, be it a machine learning model. We consider it as a perfect fit that can give us a much more better prediction. But if it is closer to 1, if it is closer to 1 or more than 1, it is considered as a poor model. That means maybe there's a problem of underfitting or the problem of overfitting. Those are the simple problems that we could experience when we are taking estimations. Now, the next one is the mean absolute percentage error. You can consider it as number 3, the mean absolute percentage error. mean absolute percentage error. So the mean absolute percentage error is an approximation of the previous one, in the sense that it will run from I equals to 1 to n, all of them I equals to 1 to n. I equals to 1 to n, yi minus yi bar divided by yi bar. That is the approximation for the mean absolute percentage error. Now note that this is y bar, and that y bar can be given as the average of the observed data set. It's a better approximation of the observed, but some people don't use the average of the observed data set. The average of the observed data set, because they are dependent variable, but it's good to use them as well, because an average is also a better approximation of the data set. So you can use this, or you can use the y as well. You can use the y as well. So this is our own invention. If you want to use this, follow the normal trend, but this one is a better approximation, and you see why we said so in due course. Okay. Now the only problem in mean absolute percentage error estimation is that if the initial data set start from 0, so if this initial state start from the 0 pay like this, we are going to have the problem. We are going to have the problem of zero divisor. We'll have the problem of zero divisor. So to correct that problem of zero divisor, maybe the mathematician will say they are undefined. I think at this point the computer scientists take over from them by trying to differentiate that concept, or provide them a better solution for that, and then they use computer to create this transfer function. So the next aspect is the mean absolute percentage error, but we include the notion of tangent. Include the notion of tangent. Okay, remember, by percentage you must have 100 units there added to it, so that it becomes a mean absolute percentage error. There is a 100% in it. Now for the threshold is the same. It should be less than 0.01. Some people consider it to be just 10% of the data range. 10% of the data range. So the next one that we should consider is the mean arctangent. I think we can clean this one. The mean arctangent. The mean arctangent absolute percentage error. Mean arctangent absolute percentage error. So we define the mean arctangent absolute percentage error by, remember, the approximation follows using the average, n, I equals to 1 to n, by the arctangent of yi minus yi caret divided by yi, and then you take a multiple of 100. You take a multiple of 100. Now, this is a mean arctangent absolute percentage error. Is like a correction factor to the mean absolute percentage error, in the sense that this arctangent will now reduce that problem of undefined zero in the denominator to a particular range of pi 0 to pi over 2, because the arctangent is finite between 0 and pi over 2. So this is now a better approximation than this. So we normally say that, okay, it should be, the index should be less than 0.01, while others prefer 10% of the data range. Others prefer 10% of the data range. But for you to have a perfect goodness of fit, it must be less than 0.01 in the range. Okay, so the next one that we should consider is basically used for regression models. This is the fourth one. So the fifth one, I think so, is used for regression model, which is called the coefficient of determination. Coefficient of determination. You call it R squared. Coefficient of determination. So the R squared is defined as 1 minus the summation of I equals to 1 to n of yi minus yi caret squared divided by summation I equals to 1 to n yi minus y bar squared. Now you could see the difference in this case. The carets here I'm using is to represent this function here, but here this one represents the mean of the observed data. So this is going to be summation yi equals to 1 to n divided by n. So this is the mean. Now it really have a practical meaning if you are using an SPSS to generate the data. You see that in the SPSS output, you will now go down below the table. We will have R squared, which is called the coefficient of determination. Now this coefficient of determination gives you the proportion or the variances in the dependent variable, or in the predicted, the variances in the response variable as a result of the contributions of the independent variable. So what I'm trying to explain is that if you have a model like this, if you have a model like this, look at this. If you have this model here, then remember that you have these to be the independent variables. These are the independent variables, and they are finite independent variables. So we consider that in a regression model or a multiple regression analysis. So these are independent variables, which we might have given you an example by saying, okay, these independent variables could be factors affecting student performance. It could be family background. This one could be family background. This one could be motivation. This one could be learning style, and others could be maybe self-regulated concepts, attachment or peer effects, cognitive abilities, and the rest. So what are the contributions of those independent variables on the dependent variable, which is possibly the learning outcome in this case? So this equation could represent the model that we are going to create or to obtain based on this data set to define the y carried to be academic achievements or learning outcome. It could be learning performance. That's those discrepancies have those terminologies have their different meaning as the case may be. So this one depicts the learning outcome, and this one depicts learning factors that affects learning. Excuse me. Sorry for that mix-up. So as I was saying, we now have this function to define the respective input variables and the output variables. So this is the response variable, in this case academic performance or learning outcome. Then we have the factors that could affect student performance, which we have mentioned several of them. So this forms a simple regression model, a multiple regression model as the case may be in this case. So the coefficient of determination then is going to enable you to identify what is the overall variance contributed by the learning factors on student academic performance, and it to convert it to percentage, So what we are saying is that this one lies between the index lies between 0 and 1, but by percentage as well. So the higher the percentage of the coefficient of determination, the more effective your model is. So if you have, for instance, maybe 60% contribution of the independent variable on the dependent variable, you now say, okay, that model is good enough, but it's only maybe 40% of the factors of other factors that you did not consider in the measurement, or you did not consider in the analysis. Then it could be extraneous factors, it could be some miscellaneous components that can also predict student performance. But at least you have been able to see that that these factors we have considered so far contributes 60% of variations in performance of academic in performance of student academic achievement or learning outcome. So that is the function of the coefficient of determination. It is very important for those that use regression model in educational analysis. Now, you should also take note to the fact that this coefficient of determination is the same as the correlation coefficient once you square it. Once you take the square of this coefficient of determination, it becomes once you take the square of correlation coefficient, it becomes a coefficient of determination. So for instance, you have this, you have the correlation coefficient between a bivariate data set like this. Maybe you are given a data set, say x, y. This is another way of forming the data set. You can say x1, y1, x2, y2, like that to xn, yn. Now this is the correlation coefficient between these two data pairs, which is n summation xy minus summation x summation y. divided by square root of n summation x squared minus summation x all squared. You close the brackets, you divide it by, you multiply it by n summation y squared minus summation y all squared. You close the bracket. Remember, it runs from I equals to 1, from y equals to 1 to n, and the range is 0 and 1 for any positive relationship that you want to have. If you obtain this r, from this data P, rxy, and then you square it. If you square it, it becomes coefficients of determination. Yes, becomes coefficient of determination. But in this sense, it's just a linear regression model. It's just a linear regression model. Now, void of any error in it, or the interception, as you may call it. So that is how to convert it to a coefficient of determination, and it helps you to also interpret the data effectively, and also tells you, okay, my approximation is good enough, is a good fit. I can proceed to use that model in the test set, because all of this one, for instance, if we're considering machine learning, these ones are called the training data sets. So if the model fits very well, you can then use that model to extrapolate. You can use that model to extrapolate your decision using the test data sets, and that will help you to make informed decision. Now, an approximation of the coefficient of determination is the adjusted coefficient of determination. That is another estimation index that you can use to improve the accuracy of your data set. It is called the adjusted R squared adjusted value. So it is defined based on the correlation, the coefficient of determination by 1 minus into 1 minus R squared. Then you multiply it by n minus 1 divided by n minus k minus 1. Now this n is a sample size, or the sample data points is the sample size, and then k is the number of the independent variables. Number of independent variables. Now you compute it using the coefficient of determination that you have obtained before. So invariably you can also obtain the adjusted value for a linear regression. If you proceed this same way, you can obtain the adjusted coefficient of determination for even linear model as well, or linear regression. Example, the correlation obtained from the Pearson products moment expression or formula. Okay, now the main thing is also for you to note that this one lies between 0 and 1. So it is the higher it goes, or the closer it is to the number 1, then the better the estimation. So you can express it in percentage as well by multiplying by 100, convert it to percentage. Now, what does this R adjusted value do? These are the questions that we ask some of our PhD students, master students during their proposal presentation, to tell them, okay, this is what it means. Now, what does this R adjusted value do in your analysis? For instance, you have been able to use some variables, some independent variables which I have mentioned before, some factors that could contribute to the improvement on student performance. And then you decide to adjust. You decide to adjust those independent variables by adding one or two hierarchically, by adding maybe pre-test scores, or by adding maybe another concept or another construct like gender effects to see the sensitivity of that model. So what this adjusted R squared does is to penalize the model in respect. So sometimes we call it the penalizer. So it penalizes the model in respect of the new parameters or the new constructs you have added. So for instance, if before you add the new parameter, you have the R squared value of 60% and the R squared adjusted value of maybe 62%, but when you decide to add some other variable hierarchically into the model, you begin to see change in this coefficients. For instance, the R squared will now increase from 60 to 61%, and the R squared adjusted value increase. Maybe initially, if it was 62, it could increase to maybe 62.5%. So it means that this new variable that you have added, maybe you added pre-test only, it means that this new variable that you have added improves the power of the test statistics. That means it improves your ability to identify possible significant difference or possible significant effects in the model. So it penalizes this model positively, in the sense that there is an increase in the coefficient of determination. So that particular factor contributes positively to the precision and accuracy of that model. So you can then proceed to add it. But if you add more than two, and then you see that difference, you need to conduct maybe a post hoc to see which of them really contributed to that significant increase in student performance. Obviously, it increased the power of the test statistics. It increased the power of the test statistics. So that means it increased the chance of you being able to detect a possible error, or the chance of you being able to detect possible significant difference. Yes, possible significant difference in your analytics. Then the next one, obviously the error threshold is in percentage. So if it's close to 1, it's better. If it's close to 100%, it's better. Or if it's close to 1, based on the Fusi parameter here, it's a better prediction or a better estimation model. So you can proceed to use it to train or to conduct analysis, or proceed to use the test data sets and then continue with your analytics. From there, you make informed decision about the model you have created. Now, square goodness of fit. The chi-square goodness of fit model. Now, this one is also a test statistics as well. The chi-square is a test statistics, and it really works for categorical data Yes, it works for categorical data, or head count. It works for head counts as a test statistics. But you can also use it as a way of estimating the measurement error in your analytical tool. So we define it as the chi-square equals to, you take the summation of the observed value minus the expected value all squared divided by the expected value. Remember, if you obtain the chi-square contingency table, the degree of freedom will now be maybe n minus k, where n is a sample size and k is the number of the independent variable. Or you have the degree of freedom to be rho minus 1, column 1, column minus 1. So this is also the degree of freedom in this test statistics. Now remember how to obtain this expected value. The expected value is the column total and the row total divided by the total number of response. Total number of response. So that is how to obtain the expected value. Now after computing the chi-square, it's a chi-square computed value, it is going to be related with the probability value, which is the p-value. The p-value is always less than 0.05. If you are taking 0.05 level of significance, that means you give yourself a 95% interval of committing type 1 error. So in this sense, the chi-square, if it is greater than the p-value, if it is greater than the p-value, that means it's greater than the 0.05. If it is greater than 0.05, you now say that okay, the discrepancy between the observed value and the expected value is not significant. So it also gives you a way of being certain about the measurements you have taken. So fundamentally, these are the basic estimation tools that you can use to confirm whether the machine learning you are going to use or the analytical model you are going to use is going to be effective, or is going to give you a good prediction. It's going to give you a good predictive decision based on the data you have gathered so far. So these are the fundamentals of educational analytics. Now, subsequently, in the subsequent lecture, we are going to consider possibly the performance index or performance indices, because these ones that we have considered today, they are only used for the training data. The training data, we don't consider the test sets. We don't consider the test aspects. We only just want to see how did the model predicts the training data set. But you can also use it for the test data. That means you can use it to make like interpolation. You can use it to interpolate the test data sets as well. So these are the fundamentals as well. So maybe in the next lecture we can consider performance indices, which help us to check and then cross-validate. Yes, to check and cross-validate different kinds of models, because we have so many of them. Example, we have regression models, which is very much useful in educational sciences. We have regression model, we have analysis of covariance, we have the hierarchical models. Then these ones are fundamental in educational analytics, but in machine learning analytics, we have the neural networks. We have neural networks, we have deep neural network, we have the CNN, convolutional neural network, we have k-nearest neighborhood, that's for maybe cluster analysis, and other ones that could be used. So irrespective of these analytical models that you are going to choose or you are going to create, because recently we have this physics inspired neural network. Then we now have a biology inspired neural network. So these ones are recent ones that have just been introduced. Of course, I'm not so much familiar with this biology inspired network. So they are the recent one. So we are going to use these performance indices to cross-validate how these analytical models function, whether they are effective in the model or whether they're effective in usage depending on the data set, or which one is much more effective than the other. Which one is much more effective than the other? For instance, we just derived one simple technique to conduct validation, to carry out validation. Initially, validation was just face validation. We don't have values for them, but we can derive techniques. We can derive techniques to conduct a validation of our instruments. Maybe what if you assign scores, or if the validators assign scores to your instruments based on its assessments, you can construct a model. You can construct a model and then give it a name, maybe eta value model. You can construct an eta value model to use and then measure the validity index of those validators. How will you be able to know if the new model you have created is functional or is efficient? It will be through comparing them with the existing ones. And how will you compare them with the existing one? It is the estimation indices that will help you to do that. I think that is the main essence of the lecture. If you create your own machine learning model, how will you validate its performance? How will you validate its efficiency, precision, and accuracy? If you understand the concept of error estimation, it will help you to solve that problem, and you can have your own algorithm to train or to use for your analysis. Yes. So that is the end of today's lecture. Subsequently, we'll consider performance indices in our subsequent class. Thank you so much for listening.